Welcome to Physics with Mr. Brazil. Today we're going to tackle conservation of energy. We got a sled that's 25 kilograms sliding down a frictionless quarter pipe, and it's going to fly out into this water that's below 15 meters. The pipe itself also has 15-meter radius, so we're going to use conservation of energy and projectile motion. Also, we're going to compare to this on another planet and what happens. So let's give this a try. First of all, let's take our conservation of energy. What's sweet is that the radius, if we put it vertical, that's 15 meters. That's a 15-meter drop above the other 15 meters. So we can use conservation of energy to determine the exit velocity, which is going to be our Vx naught, and that will tell us where this object's going to land in the water, some x direction, or delta x, okay? So, first task, conservation of energy. At the very top, we do have potential energy. That's our initial. We also have no initial kinetic energy, so that's 0. And that will be equal to the final potential energy, but we're only taking it at the end of the quarter pipe, so that will be 0, because that's going to give us our exit velocity, the energy due to that 15-meter height. And I'm not talking about the 15 meters below, I'm talking about the radius 15 meters. So our kinetic energy final. Let's write our equation. mgh equals 1/2 mv final squared. Okay, masses cancel, and v final equals 2gh, and we'll square root that and put some values. So negative 9.80 meters per second squared times negative 15. And that's because, let's put our coordinate plane right at the end of the quarter pipe, that's 0. So therefore, in the y direction, y final, that's going to equal negative 15, if you could see right below the question itself. Negative 15 meters below. Back to the bottom here, square root, and that's going to give us a velocity of 17 meters per second. Okay? With that knowledge, we can now determine the time that this thing is going to, sled is going to take to fall the 15 meters below the quarter pipe. So using our kinematic equation, y final equals y initial. Y initial is 0 because we put our coordinate plane at the end of the quarter pipe. Vy initial is 0 because it's just at that very top point. There's no velocity in the y component, but we do have 1/2 gt squared. Well, solve for t, we're going to have 2y final divided by g, square root. Let's put in our values to get a time. So negative 15 meters per second over negative 9.80 meters per second square root that, and we're going to get a time of 1.7 seconds. Okay, let's now find our horizontal component, because this gets kind of exciting. So I'm kind of color coding this so you can follow. Again, you could always slow down the video. You can pause it. Try to do the math yourself also, so don't just leave it up to me. So x final equals x initial, which x initial is going to be 0 anyway, but plus Vx naught. Well, guess what Vx naught is? Vx naught is the 17 meters per second. Let's put Vx naught down there. Vx naught. See, it's the same thing. That exit velocity due to the potential energy at the top is the Vx naught. So t, which we just found out, 1/2 axt. Well, there is no acceleration in the x component because projectile motion velocity is constant. So delta x is going to equal Vx naught t, which is going to equal 17 meters per second times 1.7 seconds. And that's going to give us 29 meters. Huh, that's kind of interesting. Let's apply this to the planet Mars. Let's take this same setup and see what it's going to give us. Let's take this question, not change any of the values, 15 meters radius, 15 meters above, and some water below. Let me make this probably a little smaller so things fit a little nicer so that we can actually see things. I'm going to move, oops. How about if I do, oh, that doesn't look very good. I'm going to try again, okay? So please be patient with me. There we go. Okay, so I'm going to leave this off to the side here where we can see it. All right, so on Mars, gravity equals, and this is Mars, equals 3.73 meters per second, okay? Well, we'll have the same potential energy, meaning the same equation. Initial potential energy is equal to the final kinetic energy. So m and then g Mars. Height is the radius. The object's mass doesn't change, so let's put 1/2 m, and v final squared. So far good. The mass is going to cancel. So final, and I'm going to call this Mars, let's put that Mars also m, is going to be equal to 2g Mars h. So let's put some values in there. And we're going to have 2 times 3 point, and we'll say this is negative also, so negative 3.73. Should have done that up above too. Okay, meters per second squared. The negative 15 meters, just like before, square root the whole thing. And we're going to have a velocity of 10 meters, so 10.5 meters per second. All right, that sounds good. So, will this object land further away from the base? It's going, it looks a little slower. Oh no, maybe closer to the cliff? Let's see what happens. So let's find the time. So let's adjust for the time. Time will be the same as before. So let me put this in a different color. Let's try orange. So T Mars is going to be equal to 2y final over G Mars square root. So nothing's changed here much except for the gravity. So negative 15 meters over negative 3.3 meters. Square root this. And that's going to give us a time of 2.8 seconds. The time is slightly different. Okay, let's see what happens. Let's do this in purple. Okay, so I'm going to take all of this and put it up here. Delta x, all right. We're going to take our Vx initial Mars times T Mars. Okay, and Vx initial Mars is equal to the 10 meters per second that we found earlier. So that's 10.5 meters per second times 2.8 seconds. And lo and behold, you do this also, we're going to get 29 meters. Wait, the distance is the same on both planets? I'm going to tell you yes. Here's the deal. All the energy is coming from that quarter pipe and the height above the water. It is proportional on both planets, and not only that, if you do the math, you will see that gravity will drop out. Okay? Here, I will do this probably in red again over here on this side. So take a look. And we're just going to put the general equation. That's why AP Physics loves to use equations instead of just throwing numbers in. Okay, we know that delta x equals Vx final. Vx final. Let's get this as final. Okay, or the final velocity at the potential energy. Okay, we also know that the time is equal to the falling time. Okay, and if you can look back to the left here and you can see the equation. So V final is the square root of 2g, and we could put gm or any g of any planet, any height, times, okay, and we know that the time is square root 2 y final over g. Okay, well, these are two roots, okay, and if you pay attention to this carefully, you're going to have 2 times 2, that's 4. You're going to have y final times h over nothing because the g's are going to cancel. This fraction bar extends and g's cancel. So g cancels out of this. This answer is going to be 2 square root y final h. And in our case, it would be 2 times 15 meters, 30, 29, if you go to 1 sig fig. So this is an interesting concept. Please play with this. Actually, let's make this small again. See if I can do the same thing I did last time. Let's do it again. I'm getting used to using this piece of software. Okay, let's move this over here. Let's look at projectile motion. And we could do this way. I'm going to erase that paragraph, that parenthesis. And let's pick a different color. That's going to probably, let's try green. Okay, let's think about this. Here's the deal. Here, gravity isn't tossed out. On Earth, you have that a ball or mass or something that's being kicked and with an initial velocity of 17 meters. Let's use those original 17 meters. This is going to go some delta x, a parabola, del x, way out here. Okay, but due to Earth's gravity, it's going to go out further. So let's call this del xe. I don't know if you can see the e. Now let's do this on Mars. Same thing, same ball, same 17 meters per second. That's going to exert a whole different amount of kinetic energy, and we know since gravity is less on Mars, this ball is going to go way further, so delta x Mars is going to be further. In other words, delta x Mars is going to be greater than delta x Earth. Think about this and play with the math. Okay, have fun, enjoy physics, and thank you for your time. Bye.